In this video, we'll briefly look at electron configuration and magnetism. When we're looking at electron configuration, that can help us tell whether an element is going to be considered paramagnetic or diamagnetic. If it's paramagnetic, then it is actually attracted by the magnetic field. And this happens when we have one or more unpaired electrons. If something is diamagnetic, then it's not attracted to the magnetic field. In fact, it's slightly repelled. And a diamagnetic element has all of its electrons paired. So if we take the example of silver, silver is element 47. So if we wanted to write the shorthand configuration out for silver, we would think it would be silver. Krypton is the last noble gas. So we'll write krypton in brackets, followed by 5s2. And then remember, after the s orbitals, we start the d orbitals. So it becomes 4d, and silver is 9 elements in, so it becomes 4d9. So if we draw out the orbital diagram for that, I'd have 2 electrons in the 5s orbital. And then remember, the d level has 5 orbitals. So then when we're filling up those orbitals, we can see that there happens to be one unpaired electron. So this would be silver's configuration if it's a normal element. But remember, a lot of our transition metals are exceptions. So what'll happen for silver is it'll actually take one of the electrons from the 5s orbital, and that moves over to the d. So that way the d becomes completely filled. So we no longer have an unpaired electron. Instead, what happens is we have an unpaired electron that's in the 5s orbital. So no matter which way silver has its configuration, it still is considered paramagnetic because it has that unpaired electron. And so when we're looking at the magnetic properties and magnetic behaviors of different elements, we can actually use that as evidence to figure out electron configuration. And so if we take the example of titanium, titanium is element 22. If we look at its valence electrons, it has a filled 4s shell, and then it has 2 electrons in the 3d. So here, titanium would be considered paramagnetic. But now if we think titanium becoming titanium plus 2, when it becomes titanium plus 2, we've lost 2 electrons. Now you can do it 2 ways. You can either lose the 2 electrons from the 4s orbital, or we can lose the 2 electrons from the 3d orbital. So we could have also written out titanium in this sort of way, where titanium plus 2 would lose the electrons from that 3d. So if titanium plus 2 loses the electrons from the 4s, it's still paramagnetic because we have unpaired electrons. However, if it loses the electrons from the 3d orbital, it becomes diamagnetic because I have the electrons paired. It has no unpaired electrons now. So if it has no electrons unpaired, it's diamagnetic. So it had very different magnetic properties. And through experimentation, we found the titanium plus 2, so the titanium that's a charge, the titanium that's an ion, is actually paramagnetic, which means this is proof and evidence that it actually loses the electrons from the 4s instead of the 3d. So titanium plus 2 has an empty 4s shell, but it still has 2 electrons in its 3d. So this is one way we can use magnetic properties to figure out electron configuration. Or we can also say we're using electron configuration to verify the magnetic properties. And so remember, if something's paramagnetic, it has to have unpaired electrons. If it's dimagnetic, then it has no unpaired electrons. They're all paired up. And so now you guys should be able to determine if an element is considered paramagnetic or dimagnetic just by looking at its electron configuration. You should also be able to start coming up with ideas on if an ion is paramagnetic or diamagnetic by looking at its electron configurations again.